Okay, this week we're going to be talking about moving fluids. So last week we did fluid statics. This week we're doing fluid dynamics. And the first thing we want to talk about is what's called ideal flow. So this is a situation where we've got a fluid with no friction. For fluids, friction is called viscosity. So a fluid with a lot of friction would be like honey. It's got a lot of viscosity. It flows very slowly. And a fluid with only a little bit of viscosity would be like water or hot oil, and it flows very quickly and easily, and that would be low viscosity. And what we're talking about here is no viscosity, zero viscosity, which means no friction or inviscid, non-viscous flow. We're also going to be talking about incompressible flow. And so the idea here is that the fluid doesn't compress or expand, it just stays with the same density throughout. So I want to talk a little bit about fluid flowing through a pipe, and this could be air flowing through the pipe, or water flowing through the pipe, or gasoline, or blood, or anything flowing through a tube of any kind. And what I want to talk about is something called the flow rate. And the flow rate, the symbol for the flow rate is Q, and what it means is it's the volume of water that flows through the pipe in any given amount of time. So we would measure this in meters cubed per second. That would be the standard units, but you could also measure it in liters per second or gallons per hour. The whole point is it's a volume divided by a time. But the standard unit is meters cubed per second. Now what I want you to imagine is that we've got this round pipe and we've got water flowing through the pipe. It's flowing at a certain velocity. And then if we allow time to go by, that water is going to move a certain distance through the pipe. And the distance that it will move, if we imagine that distance it moves is equal to velocity times time. Okay? So, the volume contained in that cylinder, and I guess I'll color it, the volume contained in this, can't see the blue very well, in this blue cylinder would be the total volume that passes through this part of the pipe. And the volume of that cylinder would be equal to the area of the pipe times the height of this cylinder, which is velocity times time. And so that would be the total volume of fluid that flows through the pipe. So if we want to know what Q is, Q would be the volume divided by the time, which is A times velocity times T divided by T, which means that it's equal to the area times the velocity. I drew that poorly. Okay, and so one important useful piece of information is that the flow rate, the flow of fluid through a pipe, is equal to the cross-sectional area of the pipe. Now remember, if that's a circle, then it means pi r squared. If it's anything other than a circle, then it would be some other formula, times the velocity of the fluid, how fast it's moving through the pipe. So that's an important piece of information. Now, let's look at a simulation of this. Oh dear, this is going to take a moment to load. Thought this was already running. My apologies. All right, so here is water flowing through a pipe, and what we have is, again, this is in viscid flow, so there's no friction, and we've got this fluid flowing through the pipe. And you can see the little red dots are moving along in the fluid with the fluid. But what I want to do is make one part of this pipe bigger. So let's make the opening of the pipe large. We'll go ahead and make it pretty large. Okay, so the opening of the pipe is nice and large. All right, and then it starts to get smaller, and then we can have the exit of the pipe be even smaller. Okay, so here's our situation. We've got this pipe with water flowing through it, and again, it could be any fluid flowing through any pipe, but what I want you to observe is that as the fluid comes into the skinnier part of the pipe, it has to move faster. And the reason it has to move faster is because if we have 5 gallons per second coming into the pipe, we have to have 5 gallons per second going out of the pipe. So I'm going to bring up this little meter here, and this is showing the 5,000 liters per second. That's 5 gallons, or not gallons, that's 5 meters cubed per second. So if we've got 5,000 liters per second of fluid passing through one part of the pipe, we have to have the same amount passing through every part of the pipe. And the reason is, imagine if we had 5,000 liters going in, but only 2,000 liters coming out, where would the rest of the water be going? So if there's 5,000 liters per second going in, there has to be 5,000 liters per second coming out. And what that means is that when the pipe gets smaller, the water has to move faster. In order to get that same 5,000 liters per second, we have to have the water moving faster. So we can see that over here, we might have fast-moving water, and over here, we would have slower moving water. So the idea there, the way we do that mathematically, is we say, okay, well, at any 2 points in the pipe, so maybe you've got a point here where you've got water flowing through one part of the pipe, and then you've got a part over here where you've got water flowing through this other part of the pipe, and we could label this point A and we could label this point B. The Q going through point A has to equal the Q going through point B, which means that the area at point A times the velocity at point A has got to equal the area at point B times the velocity at point B. And that's going to be another really important point for dealing with flow through a pipe. It says that the total volume of fluid entering the pipe has to equal the total volume of fluid exiting the pipe. And I hope that makes sense. If we imagine this part of the pipe between the entry point and the exit point, if you had more gallons per second going in than were coming out, it's like you'd be making water disappear, and that doesn't make any sense. So the flow in has to equal the flow out, which means area A, velocity A has to equal area B, velocity B. So if this area gets smaller, if that area gets smaller, then the velocity has to get bigger. The water has to move faster. Okay, hopefully this is still running. Okay, sort of. The other thing I want to talk about is how this affects the pressure of the water. Now, what do we mean by pressure? Let me go ahead and delete this. What do we mean by pressure? What we mean by pressure is that the fluid that's inside the pipe is pushing on the walls of the pipe. right? It's pushing out on these walls. Okay, and over here, the fluid is pushing on the walls of the pipe. And if we had a ball or something that was inside the pipe, the pressure behind it would be pushing it forward, right? And the pressure in front of it would be pushing it backwards. Right? So, this thing is being pushed on by the water in front of it. It's being pushed backwards by the water in front of it, and it's being pushed forward by the water behind it. And let's go back and look at the flow again. And imagine all these little red balls are floating along in the water. And what I want you to notice is they speed up, right? Over on the left, they're moving slow. And as they move over to the right, they're going faster. And we can see if I make this tube even smaller, we can really see how fast those guys get moving. But the deal is, here in the middle, they have to accelerate. They have to speed up. And the only way that happens is if the pressure on the left is bigger, the pressure pushing those balls forward is bigger than the pressure pushing them backwards. So here's what we're saying. Over here, we have high pressure water, and over here, we have low pressure water. And so there's a general idea here. This is called Bernoulli's principle. I almost certainly spelled Bernoulli wrong. Sorry about that. This is Bernoulli's principle. And Bernoulli's principle says when the water, or shouldn't say water, when the fluid in a pipe slows down, its pressure increases, and vice versa. When the fluid in a pipe speeds up, its pressure decreases. That is the Bernoulli principle. And we can see that in our simulation if we bring in a pressure meter and we measure the pressure. Well, first of all, if we measure the pressure outside, we get atmospheric pressure, right? 101,300 approximately pascals. Okay, but in here, the pressure is higher, maybe about 123 kilopascals or 123,000 pascals. But over here, the pressure is less than that, only about 100 kilopascals. So what we see is that the slow-moving water is at high pressure and the fast-moving water is at low pressure. And it's actually that pressure difference that speeds the water up, that helps the water get going. All right, well, there's a formula that we can use that explains the Bernoulli principle. And basically, it's conservation of energy. Because if there's no friction in our fluid, then the energy of the fluid at one point in the pipe should be the same as it is somewhere else in the pipe. And we're actually going to take into account not only the velocity of the water, but also the height of the water in the pipe. So if I have a pipe that goes uphill and also gets skinnier, okay, we can call this point A, and we can call this point B. And if we imagine a chunk of volume of this water, now of course up here it's going to be it's going to take up more space in the tube, or it's going to take up the same amount of space in the tube, but in order to have the same volume, you've got to have a longer piece. I hope that makes sense. Anyway, if we look at that volume of water as it travels through the pipe, and we think about the energy of that water, it's got kinetic energy, right? Because this water is moving, it's got a velocity. Down here, it's moving slow. Up here, it's moving really fast. So if I think about the energy of this water, it's going to have kinetic energy, 1/2 mass times velocity squared. It's going to have potential energy, mg, I'm going to call it h, I don't remember what the textbook does, but we'll call this height of the water at point A. And if we believe in conservation of energy, then it should equal the energy of the water when it's up here at point B. So that water's got kinetic energy, 1/2 mass times velocity b squared plus potential energy, mg height b. That's the gravitational potential energy. And it turns out we just need one additional kind of energy to make this work. Because it turns out that a fluid, when it's under pressure, has potential energy. And I hope that makes sense. If you pump a 2-liter bottle full of air and you keep pumping more and more and more and more and more and more and more air into it, eventually that's going to explode, right? And when it explodes, it's got a lot of energy. And so a pressurized fluid has energy, and that energy is equal to the pressure times the volume. So we actually have 3 kinds of energy that we need to keep track of: the pressure energy, the kinetic energy, and the gravitational energy. And if we add up the total energy at point A, and set it equal to the total energy, that makes sense. They should be the same. And the reason they're the same is because there's no friction, so there's no energy lost to thermal energy or anything else. Okay, but this is not the way the formula is usually written down. The way the formula is usually written down is we divide this whole formula by the volume of the water. And so then we get Bernoulli's equation, which says that the pressure at point A plus 1/2. Now, if I divide mass by volume, I get density, 1/2 density times velocity at point A squared plus density times g times the height at point A is equal to pressure 2 plus 1/2 density times, pressure B, 1/2 times velocity times density times velocity v squared plus density times g times height at point B. And that is Bernoulli's equation, and it is useful for figuring out how the pressure changes between any 2 points in a pipe if we both go up and down a hill and we have a pipe that's where the fluid's getting slower or faster.